Morning, all. Let's wait for a couple. It's still early, so. Malia, yeah, I saw your chat. Let me answer that once we get more people here. I can say a couple things about the test. I got to fix the network. Hold on a second. All right, let's just wait like another half minute or something for stragglers. I have 0 people with their camera on this morning. Somebody must be bold enough. I can't teach to just 150
Gotta set up my camera. I have the only laptop on Earth that
dark
didn't come with
squares
one.
with names on them. That's fine. I'm just going to turn my camera off. No, just kidding. Oh, good. All right, there we go. Shamed into it. So, Liam, how come you always get put in a waiting room when you arrive?
No idea.
You're muted.
So
Oh, wait,
sorry.
no, you're not muted, but I'm no volume. Sorry, go ahead.
I'm really sorry. I have no idea.
Huh, no, it doesn't matter. It's not a problem. It's just funny. It always happens only to you. I don't know if like something weird.
Yeah, and I had to make sure I was signed in with my school account, and I
Yeah.
am. It's the weirdest thing.
Yeah, I don't know. Every day I see Liam Cook is in the waiting room. So I don't know what's in there, but so Christina, can you hear yet? Christina K? Yeah, check to make sure I think other people can hear me. All right, good. All right, so I don't want to spend a ton of time talking about the test. I will post an old version, an old test, and solutions to it. Yeah, so it'll be on what day? It's not today, a week from today. And it's on material chapters 5, 6, 7, and 8. So up through and including capacitors, which we'll do today, continue today, and then probably have to do a little more of it Thursday. And the problems will look a lot like quiz problems, which tend to look a lot like homework problems. There's nothing mysterious when I make the test. All I do is I pull up PDFs of all the homework problems, and then if one of the homework problems was I don't know. I remember one, right? You did this problem. Find the electric field here from a line charge. You did that as a homework. One year, I don't know, one of the exam problems was this line charge plus another line charge here. I think maybe this distance was D and this distance was 2D. Find the electric field there. So it's, if you were good at doing this problem, then you can do that problem too. And there you have two different vectors, and then you add the two vectors. So there's nothing, 1 year, I don't know, one of the, you did this problem, I think, find the potential there in the middle of a circle. I think 1 year an exam problem was the circle now goes around 3/4, right? Or sometimes right? So it's not, I'm not trying to make questions that you'll look at and you'll say, whoa, what chapter is that from, right? They will look like homework problems, but not be the same as homework problems, all right? But the same concepts, right? Let's see, any other administrative questions before we start? Either in, I guess, let me check chat window
Yeah, someone in
too.
the chat asked, how would we submit them? Would we doing it like a PDF like we do for the quizzes, or
It's a great question. I don't know for sure. I think we're going to try. Last year, in the midst of the start of the pandemic, we did like multiple choice, which is a pain. Students don't like that because there's no partial credit. And so we may try to do just, PDF like the quizzes. I don't know that the time, Tyler, it'll be the full class. And so it'll be the full class length. And I don't know how many questions, typically, probably around 4 problems, something like that. And most likely I'm not sure it'll go this way, but most likely I'll have the file of the PDF available on Dropbox, and then you'll just download it and start working on it on paper. And then you'll submit it the same way you submit questions. So yeah, Trevor, around 4, something like that. Each one will have a few parts, sort of like homework questions. So that's what I'd guess. It depends how long. If we write it and then it looks like it's too too long, then we'll trim it down. And yeah, so Mason, you do. You have to, for the classes, you don't have to have your camera on. For exams, you do. I'm not using that. There's some system the university has where it like the camera looks and sees if you're looking around or something, and then flags and records that's too Orwellian. We're not doing that, but you do have to have your cameras on. And so yeah, there was a problem last year with some people using does the camera face you or your paper, what you're doing? There was a problem with exactly that, but we can cover more details later. And I have one really important question. So in Name That Tune last class, I know that Alex MW got 2, Jordan do. I have somebody, I was writing these down quickly, and I have 1 point for an Abby, but I don't know which. There are a couple of people named Abby. So if you got a point and your first name is Abby, all right, Abby Mott, excellent. I want to make sure you get full credit bragging rights. So, right, it's a running tally. Currently, Alex MW, I was writing fast, is in first place with 2 points. Jordan, JP, Abby Mott, and Brady Madden each have 1 point. And so, all right, so we should start. Thank you. All right, 4 people with their camera on out of 112. That's awesome. That's fantastic. All right, so where we left off, so I got to move this so I can see people and also chat. Need a bigger screen. So this way. Sorry, still moving windows. Okay, so where we left off, we were in the middle of talking about capacitors. And what we had done is we said, look, you take some voltage V, which has units joules per coulomb. So maybe it's 9-volt battery, a 12-volt battery, 110 volts from a wall outlet, but certain number of joules per coulomb. And we always write batteries with a long a long bar and a short bar. This is the positive potential side. This is the ground side. So if it's a 9-volt battery, this spot is 9 volts higher than that spot in potential. So this would be the plus side of the battery. And then if you wired that to a capacitor, capacitors we always write as 2 equal sized parallel plates. Capacitor is an object that has a certain amount of capacitance. And it's a sensible name because it involves the capacity of the object to store electric charge. So what we know is that if the voltage difference between this plate and this plate is V volts, then everything in red is at V, a potential of V, because it's all one piece of metal, right? You have a metal conductor, you have a metal wire, and a metal conductive plate for your capacitor. So what will happen is this side will build up positive charge on it. Everything in blue is at 0 volts. And this will build up negative charge on it. And the charge will continue to flow until the volt, and then this is just empty space between the two plates. And the charge will continue to flow until the voltage difference between this spot and that spot is also V volts, whatever the voltage source is, right? Because we know this is all an equal potential and this is all an equal potential. Everything in blue is equal potential to each other. And everything in red is equal potential to each other. And red is V volts higher than the blue. And so when you're asking about the capacitor, which is a function just of the object, you're asking how much charge will this store for a given voltage across it. So something that's a huge capacitor means if I put 1 volt, let's say this is just a 1 volt battery, if I put 1 volt across it, it's going to take a ton of charge on this thing before you get 1 volt of potential difference between the plates. So if you imagine these were just ginormous, huge plates, you can see that this would be a large capacitor. Because if I wire this to this thing, it's going to take, when I just run a little bit of charge onto it, fine, I'll have a very low charge density sigma because I've only run a little bit of charge on it. So I'll have some plus sigma there, some minus sigma there. These are huge plates. And so if I put just a little bit of charge on them, the charge density, because they're so big, their area is so large, sigma will be very small. And we know the electric field between the plates is sigma over epsilon naught. So if these are gigantic plates, there's only going to be a small electric field between them, which means the potential difference between those two plates will be small. And that won't be enough to get 1 volt. So if I have huge plates here, it's going to take a lot of charge before I get enough sigma, enough charge density to get a big enough electric field to make 1 volt of potential difference between the two sides. Right? So what we found, so capacitance is defined as Q over V, the number of coulombs it takes on the plates in order to get a volt of potential difference across them. And so we derived for parallel plates, if you have 2 plates like this, right, you get, so side view would look like this. That's terrible, even for me. Hold on. Right, so you have 2 parallel, let's just do them like that so I'm not touching. So there's some distance d between them. And they each have surface area A, and so there's an edge view of them. We derived that the capacitance of this object is epsilon naught A over D. That's how much charge you need to put on them in order for each volt that you want across them. Put twice this amount of charge on them, and you'll have 2 volts of potential difference across them. Okay, so we derived that last time. And there are a couple of, one of the videos I posted has a derivation of the capacitance of concentric cylinders. If you had a cylinder of radius A and then an outer cylinder of radius B. How much charge do you need to put on it? Plus charge, say, on this one, the outer cylinder, and plus charge on the outer cylinder, minus charge on the inner cylinder. How many coulombs of charge do you need on these for every volt of potential difference between these things? Right. So there's a potential difference, because if you put plus here and minus on the inner cylinder, then you're going to have an electric field that points inward. And so you'll have a potential difference between the two sides. Right. It will take you some amount of work, some number of joules to move 1 coulomb of charge from here to here. So that's the potential difference. And so on the video, we go through and derive the capacitance of this shaped object. So capacitance is a function just of the shape, the size and shape and arrangement of the object itself. Right? And again, that's why you can go into a lab and you can pick up some object and read the stamp on the side of it that tells you how many farads the capacitor is. You don't need to know what kind of circuit it's in, how many volts are across it. It's a function of the object itself only. Okay. So questions so far?
And I just have a small question about this, just kind of a conceptual understanding.
Yeah.
This is kind of from last course as well. In terms of A, so is the A the area of both plates or just one of them?
Just one of them.
Okay. And you're calculating capacitance from one of the plates or of the whole system?
No, that's a good question, right? The whole system. It just, you have, I guess you could say, all right, if you have one plate A and another plate of a different area, what's the capacitance? That would be trickier to do. That would actually.
But we always assume they're both the same area.
Yeah, in the case of parallel plates, this one has A and this one has A, and they're a distance apart. And another similar related question that often comes up is, what do you mean by Q? The total charge on this thing is 0, but that's not what we mean. We mean, when we say a charge Q on it, we mean plus Q up here, minus Q on there.
So we're mostly talking about the positive plate, which is the one that's actually going to be charged.
No, they'll both get charged. This one, when you hook this thing up, this plate will become positively charged. That one will become negatively charged.
Mm-hmm.
Yeah. Okay. Does that make sense, Eric?
Kind of.
What else?
I'm just trying to understand the situation and why you'd be using only one area.
Oh, well, you could use whatever you wanted. If you wanted to define this in terms of the area of both of them together, you could, but then you would just wind up with if you counted both of their areas, when you actually calculated the potential difference, you'd wind up with a 2 in the denominator that would cancel it out.
Okay.
Right. So, we said, let's just say that they each have area A, and we'll just go from there. And then with that assumption, we found that this was the capacitance.
Okay. Yeah, looking at my notes that we did last time, this makes more sense now. Thank you.
Yeah, okay. All right, so what else? Okay, so capacitors have a lot of uses for now, and we'll get into others as we go, but for now, right, you can think of them just as objects that are used to store charges in circuits. Obviously, well, the example everybody knows is, defibrillators are giant capacitors. They're used in circuits, though, to hold voltages steady. When we get into talking, we can't do much yet, but when we talk about more circuits, we'll talk about that. So capacitor, because it's storing charge, it is also storing energy. And so it's storing energy. Right. And so what happens is, in a capacitor, you can, over time, and we don't know enough circuit theory yet to talk about how long it takes, but if I wire this capacitor to some voltage, it will take some time before this thing charges up. So now you'll have two charged plates. And if I disconnect it from the battery, I can just leave these plates over here, right, with two wires hanging off of them. This is all at one potential, V, relative to this. So there's still the same potential difference. And if you attach this to something else, like, I don't know, whatever, you put this across a light bulb or something, it will then discharge through the bulb or through your finger if you touch it. In fact, this is why if you ever open up any electrical appliance and it's unplugged and it still says, don't reach your fingers in here, it's because there are capacitors sometimes large capacitors in electronic devices that after they've been plugged in, they then hold electric charge. And if you touch them, then it discharges through your finger, right? And so you can still get shocked even if something is unplugged, if it has a large capacitor in it. So in terms of, and the advantage of them is that they can, while this batteries and things have a limited rate at which they can deposit energy, once you have a pair of charged plates, you can deposit the energy very quickly, right? You can dump the energy that's stored in them. In other words, when you hook it to something and the current flows, this can deliver the energy very quickly. So it's the electrical equivalent. Capacitor is in some sense the electrical equivalent of taking a mass. When you're charging it up, it's the equivalent of pushing a mass up a sloped hill with some motor, and then discharging it is shoving it off the end of the cliff where it'll fall quickly, right? So you can discharge capacitors much more quickly than you can charge them up. So you charge them over time, and that time is something we'll talk about when we get into more circuit theory. And then you push them off, you push it off the edge, you discharge them quickly. So in a defibrillator, that's what it does. You charge a capacitor in the thing, and then you release the charge all at once to make a large current. And the energy is conserved in doing that. Just like here, you have to supply a certain amount of energy to bring the mass from the ground up to this peak. And then when you shove it off the cliff, it falls quickly and you get all that energy back. But they're not exactly the same thing. The energy is equal. Between these two halves, sliding it up the cliff and pushing it off, but the power is unequal. By equal, I mean, the two halves going up and then pushing it over the edge. There's a lot more power in a falling mass than there is in one being slid up this way. Right? So for this, remember, and this is something that comes up a lot in this course, do not confuse energy with power. Energy is joules. Power is joules per second. Right? So power is the rate at which you either store or spend energy. So a car that has, I forget, 746 watts. So joules per second, watts. And then about 750 watts is equal to 1 horsepower. So this matters a lot for us and a lot of real world electrical applications, right? You need to know the wattage of something because you need to know the rate at which it can supply energy, not necessarily just the total amount of energy in something. So, right, when this thing is up here, it has a certain number of joules that's stored. And you can, if you slide it down this way, it will be lower power on its way down because it will return the energy more slowly than if you shove it off this cliff. Right? So the energy is the same either way, but the wattage is very different. So for example, the only difference between you standing on the side of the road with one of those little crank jacks, if you have a flat tire and it takes you 5 minutes to lift your car from the ground up, 6 inches off the ground. The only difference between you and a hydraulic lift at a gas station that lifts your car 6 inches off the ground is the lift has more power. In each case, you've lifted a wheel 6 inches off the ground, and there's a certain amount of energy now stored in your car. The difference is the hydraulic lift did it in 3 seconds or something. And so it delivered that total number of joules in a very short period of time and has more power, delivered the joules in a smaller number of seconds. And so the power is different. So with capacitors, you give them energy with something. This battery has some amount of power it can supply, a maximum number of joules per second. And so it takes time to charge this up. When you put the capacitor in a circuit, it can deliver that energy back into the circuit very quickly. It has more power. So you've converted the energy into a higher power, the ability to discharge it at higher power. Okay. And we'll talk about more of the timing of things once we have to talk about resistors and other kinds of circuits first. Okay. So the next thing we need to do is to figure out how to handle circuits that have more than one capacitor. And this is, once you practice a couple of these, this is actually easier than the stuff we've been doing. And so if you're struggling at all in the course, this is the chapter you want to kind of, you want to be sure to do well on the problems, because it is easier. You can get a handle on it. Think of it as a way to catch up. So here's the question. If I have a capacitor C and I hook it to a voltage V, we know C is defined as Q over V. So it's pretty easy to say, well, what's the charge stored on this capacitor? I hooked the capacitor of capacitance C up to a voltage of a battery of voltage V, and I want to know the charge. Obviously, the charge on it is just C times V. So that would be the charge that is stored on that thing. If it's a huge capacitor, that's going to be a lot of charge when hooked up to the same voltage battery. Okay. So here's the question. What about two capacitors in parallel? And we're going to have to talk about what we mean by in parallel. All right, so I'm going to hook up a battery of voltage V to one capacitor of capacitance, let's say C1, and another capacitor of capacitance C2. All right. So how much charge is stored in the whole thing? So in other words, I wire it up like this, and all you see are these two wires coming out. And you hook it up to a V volt battery. How much charge is stored in this? Well, to figure that out, first I want to tell you what we mean by when we say, I claim this is two capacitors that are wired in parallel. Now, what you don't want to do is say, well, they're in parallel because they're kind of like across from each other. That can get you into trouble when you do tougher circuits. Things are in parallel, and this is true in general when all circuits we talk about. Things are in parallel. That means same voltage as each other. And when you talk about voltage, you always have to talk, voltage is like elevation. You can't just talk about elevation. You talk about elevation relative to something. And you may be implying it's sea level, but still in the back of your mind, when you talk about elevation, you have to have some relative to something. Same thing with voltage. So when we say that these two capacitors have the same voltage as each other, that's shorthand for saying they have the same voltage across them, same voltage difference across their two sides as each other. So, okay, so if you look at this, why are these in parallel? Well, they're in parallel because everything in red is one piece of one connected conductor. And so everything in red is at one particular voltage. It's at V volts. Everything in blue is at a different voltage, lower by an amount V. So we'll call this 0 and that V. Well, if this is the same voltage as that, and this is the same voltage as that, then obviously the drop, the voltage difference across these two things is identical. So that is why they are in parallel. They're not in parallel because they're next to each other, right? I could rewrite this. I could rewrite it like this. C1, C2. These C1 and C2 are still in parallel, right? You can bend and stretch wires in these things however you want. C1 and, oh, sorry, I didn't wire it at all. C1 and C2 are in parallel because everything in red is at 1 voltage. Everything in blue is at the, or everything in black, let's just say, is at the lower voltage. So they're still in parallel with each other, all right? So don't think of parallel as just being across from each other. It means same voltage as each other, all right? So questions so far? And then we're going to come back to how much charge is stored on this. What's the capacitance of that whole thing? Can I think of it as the input of, doesn't go through the other one? Yeah, Asa, I wouldn't. You know, that's this. So you're asking, like, can you think of it like if it's a flow, the input of one doesn't go through the output of the output of one doesn't go to the input of the other. You sometimes can, but the trouble is that in more complicated circuits, that often breaks down and gets really hard to figure out. So what I try to do is I try to look at different areas of a circuit and see what is the same voltage as each other. You know, I just look for connected pieces of conductor, and conductors are always equipotential surfaces because you can't have electric fields in them. And so that's how I do it. And I think you should do it that way because you can get into trouble doing it other ways. So other questions so far? Okay, so we still have this question. Great. We know this capacitor of C would have charge C times V stored on it if you hooked it up to a voltage source of voltage V. But what about this thing? If I give you just these two wires, and that the blue line represents a bag, and I hand you these two things, and you plug it into a battery of voltage V, how much total charge gets stored on those? Well, we can figure that out without too much trouble. We know that the voltage across this is V. So Q1. So this is the terminology means this is the charge stored on capacitor C1. So Q1, the charge on this is going to be C1, its capacitance, times the voltage across it, which is V. All right. The charge stored on this capacitor, we'll call that Q2, the charge on capacitor 2, will be equal to C2 times V, because it is a capacitor. It doesn't care that there's something else out here in the world. All it knows is that it is a capacitor, capacitance C2, and it has a voltage of V across it. And so the charge stored on it will be C2 times V. So Q total is equal to C1V plus C2V, which is C1 plus C2 times V. So now you can see what happened is the total charge is C1 plus C2 times V, which means that this thing acts like everything inside this line acts like a single capacitor of capacitance C1 plus C2. Okay. So questions so far? All right. So if I have a 4 microfarad capacitor and a 2 microfarad capacitor, it looks like a 6 microfarad capacitor if they're wired this way. Ping wants to connect to google.com. Good Lord. I'm afraid to say no, or everything is, why would it connect to Google? Just in case Google didn't already know enough. I'm going to say, all right, if we lose this connection, we'll know that I made the wrong click. Everyone's still there? All right, I have denied Google a small amount of information and they have not canceled our class yet.
Winning.
Right, winning. Or at least, well, yeah, not really. I'm sure they're recording this anyway. Yeah, that would have, right. Okay, so good. So this thing acts like one capacitor of capacitance C1 plus C2. And I could wire, we're not going to do all this out, but right, you could do the same thing. I could wire a capacitor across this voltage of C1 plus another one of C2 plus another one of C3, et cetera, et cetera. And then, so the capacitance of the whole thing would just be the sum of the capacitors. Okay, that is for capacitors wired in parallel. So they just add in that nice, simple way. Okay, so let's, question, capacitors charge and discharge in sync. Yeah, so Christian, yeah, would they charge and discharge in sync? That's a good question. Yes, right. They will have the same. So if I take this off of the battery and I just leave it like this, yeah, that's a good question, right? So I disconnect it from the battery and I'm left with this. So I have these two wires sticking out and you wire it to something. So I would say, yes, they will discharge equally because they will always stay, everything here has to stay at the same voltage as each other, even as it discharges and loses voltage. And so they'll decline evenly so that their voltage stays the same. So in other words, if this is twice as big a capacitor as this, it will actually give off, then in that case, it will give off charge twice as fast so that the voltage across each one will always stay the same as it discharges. So it'll start at V volts, and then as it loses charge, it'll gradually drop down to 0 volts. So they will lose charge in such a way that the voltage drops across the two of them always stay together and go to 0. And I know that without having to know any details about the system or the circuit or how you're using it, because I know this is all one piece of metal and metal is an equipotential surface. And so if this one tried to get ahead, more charge would be pumped onto it from this one. You can't get an uneven voltage difference between the two, okay? Okay, if they're in parallel plates, why do they have a polarity? So yeah, Tyler, so they're parallel, but one side is going to be plus, the other side is going to be, one side's positively charged, one side's negatively charged. And they wouldn't have to, like I could take this battery and I could flip the battery over. And so I could have a system like this. So there's a polarity only chosen by the battery direction. You could wire the battery the other way. If I had C1 and C2, and I wired a battery this way, so this is the positive side, then this would be this side would be positively charged, that negative, this positive, that negative, right? So the polarity is chosen by the battery. The capacitor is completely symmetric. There's no for one direction or the other direction. All right, they're totally symmetric. And that's a little bit of a lie. There are capacitors that, for those of you who do circuits or doing more electronics, there are capacitors that are not this simple, and they are directional. They have a preferred direction, and if you plug them in backwards, they explode, which is actually kind of fun to do. But I didn't recommend you do it. So yeah, if you can probably, if you Google search tantalum capacitor on YouTube, do not search it now during class. Then you can watch people explode them by plugging them in backwards. Okay, so how do you discharge them? Does it just happen when it's connected to something that needs the energy? Yeah, so you discharge a capacitor basically when this is positively charged and this is negatively charged. If you just run a wire between them, the electrons will flow this way, or lack of electrons will flow that way. So then current will flow, and you can put that current through some device to run the device briefly. or to hold up the voltage, to hold up the current or the voltage when the voltage source lags a bit. All right. Okay, so now we know how to add capacitors in parallel. Let's try to figure out how to add them in series. And this one, it's slightly trickier. It's still not bad. So now let's look at capacitors in series. All right, so for capacitors in series, now we're going to say, I'm going to take a voltage V. Same question as before. I'm going to take two capacitors, one of capacitance C1, one capacitance C2. And same question, if you wire this up, I know if I just wire it up to this, if this thing weren't there, then the charge, the total charge inside that's pulled in would just be C1 times V, right? Just from the definition. So the charge on that would just be C1V. But if there are two in parallel, I don't know what the charge stored on this thing now is. Maybe it's still C1 plus C2 times V is the charge, total charge pulled in and stored on the whole system. And it's not. But before we do that, just like in parallel, we have to say what we mean precisely by capacitors in series. They're not in series just because they're like one after the other. Although generally, right, things wired like this often that is in series, but you just have to be careful because it can be hard to tell. So this means, series means same charge as each other. Okay. Why would this have the same charge as that? Well, if you think about it, before you ever hooked up the battery, this little stub of metal that's just not connected to anything, that was neutral. So it had there's a total charge of 0 on this little central stub, right? This thing. And so just because you hook it up to a battery, you don't suddenly make charge. There's no charge that jumps across this gap. We're assuming it's vacuum for now. No charge is jumping across here. So this whole thing remains neutral. So after it's been plugged into this and it's all settled, you know that the charge, however much negative charge is on that, that's how much positive charge has to be on this. So there's only one, and then this will be positively charged in equal amount to that. And this is forced to have equal charge to that. And then this will have the same charge as that. So Q1 has to equal Q2. All right, so the charge on the two capacitors, so they are not, they don't have the same charge as each other because they're in series. They are in series because they have the same charge as each other. That's what we mean by when we say they're in series. Okay, so how much? What is still the total charge? What is the charge on this and the charge on that if they're equal? And then obviously twice Q, that would be the total charge stored on it. And then we could figure out the capacitance. Well, to do this, we want to take one more step. What we know is that there's a voltage across this, which is V1, and there's some voltage across this, which is V2. Now, this is a slight change. Before, we said, look, the voltage on these two capacitors, when they're wired in parallel, we just have V1 is equal to V2. That's it. Because this was all one piece of metal and this is all a different piece of metal. So V1 equaled V2. That's not the case anymore. There's no reason to think the jump from there to there will be the same as the jump in voltage from there to there. What I do know V1 plus V2 has to equal V. So this is the our first encounter with looking at voltage drops around a loop. And I think it's extremely helpful if you picture voltage drops, again, as connected to elevation. So this spot, everything in black is at 0 volts. It's all one piece of wire. Everything in red is at V volts. right? Now this stub in the center is all one piece of metal. And so everything in orange is at some other voltage in between red and black. And I don't know what this drop is. I don't know how far of a drop it is from red down to orange across this capacitor. And I also don't know what the drop is from orange back down to black. But I do know that this drop plus that drop has to equal this drop over here. Right? It's exactly the same thing as if you're walking around, I don't know, you're on a map and you're walking around a rectangle through some field that has, you know, fences that go up and down and up and down. And I tell you that there's some, you know, you're going to step up when you go from here to here. You're going to step upwards. There's some big step up when you're walking around this rectangle in a field. And I tell you here, there's a step down. We'll call it D1. And I tell you when you get from here to here, there's another step down, D2. And I tell you, you step up 5 feet when you go from there to there walking around. And I say, I'm not going to tell you what D1 is or D2 is. But you know for sure that D1 plus D2 has got to be 5 feet, because what the hell else is it going to be? You came around to the same point you started, right? And so I don't know what that drop is, and I don't know what that drop is, but I know the sum of them has to be this drop. So I don't know what V1 is, and I don't know what V2 is, but I know V1 plus V2 has to be V, okay? So it's just a question of how high that middle section is. It's somewhere in between. If this is 0 and this is V, this middle section is somewhere in there. So the sum of the two drops has to be V. So I know V1 plus V2 equals V. And I also know that Q1 equals Q2. Let's just call it Q. They both have the same charge, so we don't have to identify it as, it should be capital, sorry. I'll make these lowercase. There's no point calling it Q1 and Q2 since we know there's only one charge. So we'll just call that Q. Now I know that the equivalent capacitance, this thing acts like some certain size capacitor. I don't know how much. That is going to be the charge that it stores, the total charge it stores, over the total voltage across it. Okay, and I know the total voltage across it is V1 plus V2. So this is going to be Q over V1 plus V2. But here's the place we can, where there's a trick, not a trick, but an important step, right? I know that V1, since C is Q over V, I know V is Q over C. So I know the voltage drop across here is Q over C1. So this is Q over, V1 is Q over C1. And I know the voltage drop across here, voltage is Q over C. So that is Q over C2. Okay. Now the Q's cancel out. Yeah, capital Q and lowercase q, I'm using them interchangeably. And then I tried to then fix it so that I wouldn't have capitals and lower, just call it lowercase, just variable name. So at this point, I can cancel the Q's and say C equivalent is equal to 1 over C1 plus 1 over C2. All right. So not the same simple way of adding them as we had with capacitors in parallel. Okay, so let's take a quick example. So questions so far? Okay, so we can just do sort of a simple numerical example. If I have a capacitor of 10 microfarads and another capacitor of 10 microfarads wired in series like this, what I know is that C equivalent is 1 over C1 plus 1 over C2. So here is a way you'll often see this written, and it's easier to look at it, but you just have to be careful not to make a careless error at the end. So I'm going to invert both of these sides and just say 1 over C equivalent is equal to 1 over C1 plus 1 over C2. All right. I haven't done anything, but just invert both of these. That's an easier way to remember it and to write it down. The only problem with this is when you use this to find equivalent capacitance, you have to remember to invert it at the end. And I'll show you what I mean by that. So if I have these two wired in series and I want to find C equivalent, by equivalent capacitance, I mean, what is the one capacitor that if I wanted to throw these two away and replace it with a single capacitor, what's the single capacitor that would have the same capacitance as this pair? So I know that 1 over C1, so plus 1 over C2, according to this, that's what I want. So this will be 0.1, right? I need 1 over this, so this will be 0.1 plus another 0.1, and my units are now 1 over microfarad. So 1 over C1 plus 1 over C2 is 0.1 plus another 0.1, so that's 0.2. So here's where you get into trouble, is some people then write C equivalent, don't write this down. C equivalent is 0.2 microfarads. Because we just did it, 1 over C1 plus 1 over C2, that gives us 0.1 plus another 0.1, so that's 0.2, and we're done. That's wrong, because 1 over C1 plus 1 over C2 is not C equivalent. This is 1 over C equivalent. So C equivalent is not that. 1 over C equivalent is equal to 1 over 1 over 0.2 microfarads. And then C equivalent is equal to 0.2 microfarads. Right? So it is less than either of them. And something's wrong with that. Hang on. Sorry,
Yeah.
it's 1 over that. So it's 5 microfarads. Sorry, I'm going to do this again, just because I've made a mess of it. Right? If you add 10 microfarads and 10 microfarads, this thing is equivalent to, if you add them up, you get 1 over C equivalent is 1 over C1 plus 1 over C2. In showing you to be careful not to do it wrong and showing you how you would do it wrong, I did it wrong as an educational exercise for you. Right, so you have 1/10 plus 1/10 gives you a fifth. So 1 over C equivalent is 1/5. And then when you invert it, then you get 5. So this thing is equivalent to a single 5 microfarad capacitor, right? Because you get 1/10 plus 1/10, which is 2/10. So this thing is equal to 2/10. And then when you invert the whole thing at the end, you get C equivalent is 5 microfarads. So just be careful when you invert one and then invert the other and add them. I mean, the simple way to remember is when you add capacitors in series, you invert them and then add them. And then don't forget to uninvert at the end of your adding them up. So these two 10 microfarad capacitors act like a single capacitor of capacitance 5 microfarads. So adding capacitors in series actually reduces the capacitance. Adding them in parallel increases the capacitance. Right, and we're going to do a couple other examples of this in a second, of adding them when it's more complicated. Okay, so questions so far?
Is it just a coincidence that it's divided by 2?
When these are equal, it's divided by 2. But in general, it won't be so simple. I just want numbers to work out easy for the first case. Okay. Oh, right. Yeah. So Jia Sheng. Right. All right. So Saad, you answered the question. Right. C equivalent is like the total capacitance. We call it equivalent because we say, what is the single capacitor that would act like these two wired like this? So you can either wire two like that, or you can just get one that's like this. Two tens wired that way is the same as 1.5. It's equivalent to that single. Okay. Good. So let's do another example of this. Something a little more complicated to add. So I have a battery, and I'm going to have capacitor C1, C2, and C3 wired this way. Find C equivalent. Right? Okay, so with these, and this is just some voltage I've wired across them. With these, I think it's generally easier. Sometimes if you're good at them and you've seen this before, you can just do it quickly, but generally I think it's easier to just go step by step. So I would say that C1 and C2 are in parallel with each other, because, not because they're across from each other, they wouldn't have to be. I could put C2 up here, but I want to make it look easy in this first one. Everything in blue is at 1 voltage. Everything in blue is at V. Everything in black is at 0. Everything in orange is at some middle voltage. Okay. And so I know that C1 and C2 are in parallel with each other. So I would rewrite this circuit. So I think it's best just do these step by step. I would write it this way. This is C12. So when we write our notation, and your book's notation is C12 means the capacitor, the single capacitor that is the same as 1 and 2. So we'll call that C12, wired in series with C3. All right. Dan, so when we see these questions, we should try to trace from the battery to see if they're in parallel or in series. No, I wouldn't. I mean, you kind of can do that a little, but you need to check to see if the voltage across two things is the same before you say they're in parallel. All right. Okay, so these two were in parallel, so I'll just call that C12, and we'll figure out what C12 is in a second. And then I would say, I would take this one step further, and I would say this thing is equivalent to a circuit V C123, the single capacitor that's equivalent to C12 and C3, like this. Okay, that's great, but what is C123? I mean, that's what we're supposed to find, is actually what's the capacitance of that thing. Well, what I know is that 1 over C123 is equal to 1 over C12 plus 1 over C3. Right, so this thing is 1 over this capacitance is equal to 1 over that plus 1 over that, because these two are in series. And you say, okay, that's great, but I still, this does not, if I told you what C1, C2, and C3 are, you still can't give me a value for that because you don't know what this is. But then you say, okay, C12 is equal to C1 plus C2. So we'll substitute, go back another step, and we'll say this is 1 over C1 plus C2 plus 1 over C3, where all I did was substitute C1 plus C2 for C12. So now if you know C1, C2, and C3, you can just drop it into that, and you'll get the capacitance of the whole thing. Okay. Okay, so questions so far?
Why aren't you multiplying it by V? Where did the V go?
Yeah. So if we wanted to know, let's suppose, so this is the capacitance of this whole circuit. Now, if I said, I hook this object up to a battery of volt, let's say I hook this up to a 5-volt battery, just like this. How much charge is on it? Well, C is equal to Q over V, and Q is equal to C times V. So if you wanted to know the charge stored on these, you would have to find C equivalent and then multiply it by V to find the charge on it. So the capacitance of this object, forget about this. I could just remove this battery and have 2 wires. In fact, maybe I should have done it that way. Just had 2 plain old wires sticking out and said, what's the capacitance of this object? Pretend this thing isn't even there. Suppose that line's not there at all. What's the capacitance of that object? It's this. That's the capacitance no matter what volt. I don't need to know what voltage. I could write, if this were in a lab, I could write the capacitance right on the side of this object. You know what I mean? Okay, so other questions so far on doing this?
Question 2. This time is format wise. Can you do 1 over C plus 1 and the other one instead of doing 1 over C123? So you know how you have final C EQ on the left side of the equation?
Yep.
Okay, and then next to that you have 1 over C123. So instead of
Yep.
doing 1 over that, can you just do C123 is equal to 1 over the whole mess on the right side?
Yes, yeah, exactly. Yep. So C123 is equal to 1 over C1 plus C2 plus 1 over C3. That's perfectly fine too. I mean, that is ultimately what you do. You'd plug in something and you'd get a value. And then that's where you have to be careful. People often, you plug into this and say, okay, I'm done. I got C equivalent. And they forgot that what they actually have is 1 over C equivalent. So you got to remember to flip it at the end if you're going to use this. Okay, what else? Other questions? Okay, let's do, yeah, all right. We're going to do one example, and then I'm going to I'll make a video of another example. Let's just do a numerical one here. Let's suppose I take 100 volts, and a C1 of 10 microfarads, C2 of 5 microfarads, and then C3 of 4 microfarads. Okay, and your goal is to find Q on and V across each capacitor. There's lots of techniques you can use to do this. There's one I'll show you, which is just sort of, it's kind of pedestrian. You just sort of work your way forward and then backward, and it works out very nicely. There are shortcuts you can take, but if you don't want to, you don't need to. If you look, this is exactly the same as the circuit we had before, right? We have these two are in parallel because this is all at one potential. This is all at a different potential. So the drop from there to there is the same as the drop from there to there. So these are in parallel, and these two are in series with C3. Okay, so I don't know what it's called. I just call it the forward and backward, sort of the forward and backward method. You don't really need to write that down. I don't know if anybody calls it that but me. So what that means is we're going to work our way forward until we have one capacitor, and then find out one equivalent, and then find out these quantities on that equivalent capacitor, and then use that to work our way backwards. So what I mean by that is we'll take our first step of adding those two, right? So so this circuit, we're going to change this into a circuit with 100 volts, one capacitor C12, another capacitor C3, and then from there, we'll go and we'll say, all right, that's going to be equivalent to 100 volts across a single capacitor, C123. Oops. Okay, and again, we already did this. You know that 1 over C123 is equal to 1 over C12 plus 1 over C3. And this is equal to, well, which is equal to 1 over C12 is C1 plus C2 plus 1 over C3. So if you do that out, so you can do the arithmetic, plug in 10 microfarads, 5 microfarads, 4 microfarads into that whole thing, and you'll find that the C123 is equal to 3.16 microfarads. So nothing happens to get here except just plugging in 10, 5, and 4 for those three things. And there might be a little bit of rounding, but basically it's 3.16 microfarads is the single capacitor that's equivalent to these three. Okay, so what is the charge? Let's find, well, let's look at this. What is V123? What is the voltage across capacitor 123? This single, what is it? Somebody in chat or unmute. What's the voltage across here from there to there in this circuit?
100
Yeah.
volts.
100 volts, definitely, right? It's the right. This everything here is at 100. Everything here is at 0, so that's a 100-volt drop. So V123 is 100 volts. C123 is 3.16 microfarads. Q123, so the total charge stored on that is going to be, right, C is always Q over V. So the charge stored on this thing is going to be C123 times V123. So this will be equal to 316 microcoulombs. Right, because we got 3.16 times 100, so it gives us 316, but we have the 10 to the minus 6. So that is the charge on this. It's 316 microcoulombs. So any questions so far on this? I mean, this is not the answer to the question, because the question is, what's the charge and the voltage across that and there and there? Right, we said that you're at 100 volts here and 0 volts here, and everything in here is at some middle voltage. Well, what's the middle voltage? What's the drop from there to there or there to there? And what's the drop from there to there? And how much charge is on each one? We've only gotten a little piece. All we've been able to say is what is the voltage across the single that's equivalent and the total charge on the single. But any questions on getting these? Okay, so now here, this is if you're checking your email, stop. This is a hugely important step and that trips people up. Two capacitors that are in series with each other have the same charge on each, they each have the same charge. And this is the key point, they have the same charge as their equivalent. Two capacitors in series have the same charge as each other and the same amount of charge as their equivalent capacitor. And two capacitors that are in parallel have the same voltage across each other, same as each other, and the same as their single equivalent. And so that is how we are going to work our way backwards from knowing about the charge and the capacitance and the voltage across this to learning those things from these three. So from here, what I can say, I know that Q12, I'll use lowercase, sorry, Q12 equals Q3 equals 316 microcoulombs. These two made this and they are in series. So they have the same charge as each other and the same charge as this, but I know the charge on this. And so I know the charge now on this and on that. Okay. So if Q12 is 316 microcoulombs, I know that V12 voltage is equal to Q over C. Voltage across this is going to be Q12 over C12. All right, so the voltage Q12 is 316 microcoulombs. C12 is 15 microfarads. So this will be 316 microcoulombs over the capacitance of C12 is C1 plus C2. So that's 15 microfarads. And so the voltage across that is going to be 79, 316 over 15. Someone with a calculator, check that.
21.1 if you round,
All
or
right, so let's just say 21.
21.07.
Let's just say 21 volts. Right, so you have 21 volts across this. Okay, you can do the same thing for V3. V3 is equal to Q3 over C3. So that's going to be 316 microcoulombs divided by C3. C3 is 4 microfarads. And if you do this, you'll get about 79 volts. Right?
You'll get exactly 79 volts.
Yeah. So, and I was cheating because I know that I'm going to get 79 volts from this because, so this is key point. I know in this circuit, we just found there's a 21 volt drop from there to there, but I know the whole drop from here to here is 100 volts. So if this drop is 21, I know that one's 79. So I don't have to do the arithmetic. I already knew the answer. Right? All right, so think about questions on getting these. Right, so now we know the voltage, we know the charge on this, the charge on that, and the voltage drop across each of those. Okay?
At this point, I'm just hearing numbers and letters. I still don't know how you just put the two together. For example, you have Q12. How do you just put them together and not account for the other one that's still in the loop?
So there is, yeah. So Q12, this is the amount of charge on this object. You're right, there's still charge on this, but I'm just separately worrying about, well, how much charge is on that? If you want the charge on the whole thing, you would need Q12 plus Q3, right? So yeah, I agree with you. It's just, that's not the whole thing. It's just the charge on that individual piece, because we're trying to work our way backwards and find the charge on each of these and the voltage across each of those three.
Professor, I know you explained this a bunch of times already, but would you mind just explaining it one more time?
Sure.
How C1 and C2 from the original picture becomes C12 in the second picture?
Oh, right. So all I did was I said, look, I know these two things are in parallel. And so I'm going to be able to, so in fact, I know these are in parallel. So let's just replace them with a single capacitor, and then we'll figure out how much capacitance that has. And in fact, if you look at this diagram, I deliberately made this one a little trickier to look at. This one, this is no different than this circuit. Right? So in this one, we had, right? This is the same as that. If you look at it, all that this is just bending the wires so that this comes around the side. So these two are in parallel. And so I just said, I'm going to replace these two with a single capacitor that's their equivalent. And I know that since these are in parallel, this C12 is going to be the same thing as C1 plus C2. Is that your question or not exactly?
Yeah, it's my question, but I still kind of don't get it because I don't know, I'm trying to wrap my head around the fact that they're pointing in different directions. Like the capacitor, the gap. See, I would see how like maybe C3 and C2 would be parallel, but
Yeah, okay. So this is the trick of doing. So the first thing I want you to do is imagine I can find some empty paper. Right. So the first thing you could do is, right, you can bend pieces of wire. You're not going to change anything. So the first thing I would say to do is bend this piece of wire, squeeze this a little short, fold that up so that this one comes around the side. Right. So I could redraw, and I'm not doing anything but redrawing.
the same piece of metal. Okay, that makes sense.
So I would redraw it to look like this. Right. So the only thing that happened between this circuit and that circuit is I just, I snipped off this piece of metal, I folded it up to pull that one to be around the side. So now they look more in parallel.
Okay, I get it now.
Okay. Right. Okay. So yeah, but that is the trick. Also why you can't just look at them by like say it looks in parallel or it looks in series. These are in parallel because everything here is at one particular voltage, 100 volts. And all of everything, so everything in green is at 100 volts. And everything in orange is at some lower voltage. I don't know what it is, but it's all the same as each other. It's one value in orange. And so that if everything in orange is at one voltage, everything in green is at a different voltage, that drop is the same as that drop, that voltage separation. Therefore, they are in parallel, not because they're sort of on the sides of each other, right? Okay, so now we're going to take one more step. We've made progress, right? Now we have the charge and the voltage across this and the charge on that, the voltage across this and the charge on it, right? We've got those. And yeah, somebody else wrote, because 21 plus 79 is 100. Yeah, that's how I knew this answer was going to come up 79. After getting 21 for this, I know that. You can plug it in, you'll get the same thing. Now we'll say that's fine, but the question doesn't ask what's the voltage and across some equivalent to these two. You actually wire these in a circuit and you want to know capacitors have a certain amount of voltage they can handle across them. What is the voltage across this physical object, not some equivalent object that you use to solve the problem? So we have to go back one step further, and here is the second time. So stop checking your email if you're checking your email. Do people use email? But if you use email, so this is built out of these two. And just like two capacitors in series have the same charge as each other and the same charge as their equivalent, two capacitors in parallel have the same voltage as each other and the same voltage as their equivalent. So that's really helpful because I already know the voltage across here. The voltage across this V12 is 21 volts. So that means I know the voltage across this is 21 and I know the voltage across that is 21. So I know V1 equals 21 volts and V2 equals 21 volts because they are in parallel with each other and they have the same voltage as each other and the same as their equivalent. Well, and as always, once you know two of these three things, it's easy to get the third. So we know C1, so now we need Q1. So Q1 equals, C1 times V1 and C1 is 10 microfarads, and V1 is 21 volts. So this will be 210 microcoulombs of charge on capacitor 1. So that's Q1. Q2 will be C2 times V2, which will be C2 is 5 microfarads, V2 is 21 volts. So that'll be 105 microcoulombs. Now notice something interesting. The total charge stored on these two is 315 microcoulombs. The same thing with rounding errors as is stored on this. So this and this together store the same charge as that, which they better, because there's a neutral piece of wire in between them that can't have, right? So this thing right here picked up 316 microcoulombs of charge. This one will have negative 105 microcoulombs. This will have negative 210 microcoulombs. So it balances. So the voltage drops, half the accounting has to work for the voltage drops. You're here at 100, you drop 21 volts there or 21 volts here. So now you're at 79 volts when you're on the orange. And now you drop 79 volts to get down to 0. Okay. So now we have found Q1, Q2, Q3. Where did we find Q3? Oh yeah, Q3. And we found the voltage across V1, V2, and V3. Okay. All right. And on the, I'll make a video. Of one more example, one messy example of this. I'll just make a video of it. So, so you can see another example of how to do this. Okay. And then I will see you and start pounding away on the homework. And I'll see you in class on Thursday. Somebody has a question.
Can I request something for the videos? Is there any way you can make a mini chart like this so I can see which ones are shared? So I have
can't see that thing.
Can you like that? I have like C1, C2, and C3, so I can see which ones are shared and which ones aren't.
What do you mean shared?
So like you said, for V1 and 2 are shared between, or not, they're the same.
Oh, the same.
Yeah, or something like that, because I cannot get my mind around which ones are the same and which ones aren't.
Okay. Yeah. Hold on. Let me answer. So Jack, making sure I heard it right. Capacitors in parallel have the same voltage. Capacitors in series have the same charge. Yep, that's exactly right. Except, so this is Jack's question. I would add capacitors in parallel have the same voltage as each other and the same as their equivalent. That's how we managed to work our way backwards. Once we found the voltage on the equivalent, we said, well, that must be the same voltage as these two that make, that created this equivalent. And then substitute the word volt charge for voltage. And then you can do that with parallels, with series. Capacitors in series have the same charge as each other and the same charge as their equivalent. Right. So the short answer is yes. How do I have a new message?
I have a question. Like on this the problem, like on C3.
Wait, hold on. Whoever's speaking, you're pretty muffled.
So on this question, like on C3 capacitors 3, so like on the both the sides of that is we have negative on them. So will there be a voltage drop in that? Like a C12 is parallel and C12 is in series with C3. So and C3 have negative on the both sides. So will there be a voltage drop in that?
Yeah, there's a voltage drop here from here to here of 79 volts from here to here.
Is that possible? Like in real life, capacitors have a negative capacitance.
Oh, I see what you're saying. Yeah. So this is right. This thing is made out of these two. So if you want to look at the original circuit, your voltage drop, you'll have a 21 volt drop from here to here. So it's 21 volts across this. And it's 21 volts across there. and then 79 volts across here. Right, yeah, just because this is, I see what you're saying, because this is, because of the charges, yeah, you can still have, this will be, let's see, right, this will be positively charged, this will be negatively charged, that'll be more negatively charged. So yeah, you can still get drops across all of them this way. Is that, if that's not answering your question, just come to office hours too, and we can go through it in more detail.
Okay.
And then Michael, yeah, you have a question?
Yes, I'm just a little confused. Just a little confused by the notation. So C12 is equal to C1 plus C2, but C123 is not necessarily C1 plus C2 plus C3, right?
Exactly right. C123 means C123 means what is the capacitor that would act like all C1, C2, and C3 all merged into a single, which would not be C1 plus C2 plus C3. In fact, it would be 1 over this thing.
Okay, and C1 and C2, or C12 just happens to be C1 plus C2 because they're in parallel, right?
That's right. That's right.
Okay,
I mean, we
okay.
named it C12 to mean what is the single that is equivalent to these two. And then we said, oh, these two are in parallel. So it's just, this thing is just C12 is actually equal to C1 plus C2. And
Okay, got
1
it.
over C123 is 1 over C12 plus 1 over C3. 'Cause
Okay,
these
thank you.
two are in series. Yep. Okay. All right. I'll see you guys on Thursday or in office hours. I got to go to have 5 minutes to save my voice before another class.
Have a good
Okay,
one.